Okay, so this is number 24 in chapter 9. It says rank the SN2 reaction rates for the following compounds. So the first thing, this is actually a nomenclature issue, right? First we gotta draw these, and they're all butanes. So 1, 2, 3, 4, 2, 3, 4. Well, they're actually not all butanes. 3 of them are butanes. The other one is bromomethane. So that's bromomethane. The other one is, another one is 1 bromo, 3 methyl butane. So 1 bromo, 3 methyl butane. 2 bromo, 3 methyl butane. And 2 bromo, 2 methyl butane. So those are the 4 compounds, right? The first part is just getting the naming down. And it says rank the SN2 reaction rates for the following compounds. So basically it's saying, right, if I'm going to have a nucleophile, right, a good reactive nucleophile, which one's going to react the fastest? So if I label these A, B, C, and D, and like all these ranking problems, right, my advice always is to find the very extremes, right? So which one's going to react the fastest, do you think? Any primary would, but then, so if we have an option, right, so let's label, so what's the first question we always ask ourselves, right? We should say what type of alkyl halides these are. This is a primary, this is a secondary, this is a tertiary, this is also a primary, but it's only a methyl, right? It's pretty, as far as primary carbocations go, it's the most primary, right? It's only 1 carbon, right, versus all this extra carbon stuff here versus just 1. So I would probably rank D as the most reactive, or the fastest rate. And then which one do you think is going to be the slowest? C, the tertiary one. And then between A and B, which one's going to be faster, A or B? A should be faster, and then B. So the tough part of this problem probably is just actually drawing them out, the nomenclature part. Once you kind of see that, then it's kind of good to go.
Why would it be the fastest? Just because of the primaries?
Yeah, so both of them are primary, and then it's just a matter of less stuff to get that backside attack. And C or D only has 1 carbon there,
Okay. And
so
then
it's easier.
B and C, why do they choose that?
Just based on sterics, based on secondary alkyl halide, right? So this carbon is bonded to 2 other carbons, this one's bonded to 3 other carbons. So to do an SN2 for that backside attack, we want less steric bulk around it. All right, taking a look at number 26, chapter 9. You're given this as your starting material. Okay. And they're telling you it's 2R, 3S, so they're even telling you the stereochemistry. Nice. And they're telling you it's 2 bromo, that's all you really, once you know it's 2 bromo, 3 methylpentane. So they're telling you this stereocenter is R, and this one is S, right? Yep. And they're saying, okay, you're going to have this nucleophile in there. They also write it like this, but you should be able to recognize both forms, right? The same. And they're saying it's concentrated. Okay, so that's good for an SN2. So what happens in an SN2 reaction? Stereochemistry gets inverted. Now, what happens, is anything going to happen to this carbon at all? No, nothing's going to happen to it. Now, I usually like to rotate this bond a little bit to get the bromine to be in the plane. But if you don't want to do that here, you don't have to. So if the bromine's coming out, the nucleophile is going to have to come from where? The back. So the H is going back, and then the H is going to end up having to become front. So if we look at the mechanism, right, it attacks, bromine leaves, this carbon doesn't change at all. So let's not change it. Let's even number them. Heck, 1, 1, 2, 3, 4, 5. So it was a pentane. 3, 4, 5. Carbon 3 didn't was not. Does any arrows go towards carbon 3 or mess with it? Then you don't change it at all either. Don't mess with it. 2 and 1, and we said what do we want to be wedged right now? Coming at us should be what?
Hydrogen.
The hydrogen. Very good. And coming away from us should be the O ethoxide, right? The ether part, right? Notice, right, one people want to do is they want to break this bond for some reason. I never understood that. They really want to break this carbon-oxygen bond and make this an OH. Don't do that, right? I don't know. Right, the electrons are what's attacking, right? This is not part of the mechanism, right? If there's no arrows there, don't change anything, right? Just like this carbon is not involved, don't change anything. So what was R is now S, and this stays S. All right, going to take a look at number 7 in chapter 9. Number 7. It says rank the nucleophilicity of the indicated species in ethanol. That's the key. So we're in number 7, chapter 9, and the question is, we have these, I'm going to start drawing out these nucleophiles. In water, it's going to say either water, ethanol, it's going to be a polar protic solvent. No matter what, it's going to be a polar protic solvent. So let's draw these out. There's that guy. This guy. But it's drawn. This one's drawn. COO minus. But you should be able to see them both ways and recognize that. And this is drawn like this. And we're saying it's in a polar protic solvent. So the example they use is ethanol, or they showed water, I guess, is one of the possibles. So a polar protic solvent. Now, so we got that out of the way. Polar protic solvent's on there. What's going to be important? So like just ranking the nucleophiles. I'll number them. Letters this time. Just like last time. A, B, C, D, and E. So let's try to rank them the worst to the best, or at least group them. So which one's going to be the worst nucleophile?
E.
I would say E. Why'd you say E?
Because it's a stronger acid between.
Well, you said it right there.
It's a stronger acid, meaning
Our
the
acid is
conjugate base is going to be
But it's
more
not-
stable.
But we're not talking about the conjugate base. We're talking
We're
about
talking
the acid. It's carboxylic acid. Are acids nucleophiles in the first place? No. So you just said it right off the bat. So that's the worst. That's 5, right? What else? What would be C would be the next worst, right? Right. Well, it's an alcohol. It's not an acid. But the thing is, right? A strong nucleophile, more electron rich, right? So you can easily say those two guys are the worst, right? Easy. What's the next worst? You should be able to tell me the next worst one. D. Why D? So what's that mean? Resonance, right? D has resonance. So let's put, that's stabilized because of resonance. Now's the tough part. Sulfur and oxygen. So same sterics, right? Both methyls. So we look at the periodic table. We see where oxygen and sulfur are at. Sulfur's lower on the periodic table. So it's less electronegative, but it's also
More willing to give up.
it's also bigger, right? I mean, in a polar protic solvent, what's the most important factor? In a protic solvent, what's important? Size, right? Remember, in a polar protic solvent, the nucleophiles are going to start to get surrounded, right? So the bigger atom, harder to surround, right? The bigger the atom, the harder to surround. And in a protic solvent, it'd be different, right? In a protic solvent, then B would be the best. But in a polar protic solvent, size is the most important factor, not electronegativity, right? Size is the most important factor. So in a polar protic solvent, this is ranked number 1, this is ranked number 2. All right, we'll take a look at number 16 in chapter 9. So in this one, we have T-butanol, and it's saying we're going to react with HCl. There's only one equivalent. And it's telling us, it says, for the following SN1 reaction. So we know it's an SN1 reaction. So we know that we're going to form a carbocation. Draw the organic and inorganic products, organic meaning carbon, inorganic, no carbon. Identify the nucleophile, substrate, and leaving group, and determining the rate limiting step. Well, we already know, if you know about carbocations, what's the rate limiting step? Or, well, they already said it. If you know about the SN1, what's always the rate limiting step? Carbocation formation, right? So what's going on here, though? So this is a little different than you guys have seen before. We're starting with an alcohol. We're not making an alcohol, we're starting with an alcohol. It is an acid-base thing. So it's just like the reverse of what we've done, right? You've seen us take tert-butyl chloride and make it into T-butanol. And so you've seen all those steps, but now we're just going to do those steps in the reverse order, right? So in this first step, what's my electrophile, what's my nucleophile? So if you don't know one, if you know one's one thing, the other thing has to be the other thing, right? So look at HCl. What do you guys know about HCl? Strong acid. What are acids always? Electrophiles. So what does the other thing have to be? So where is it electron rich at? On the lone pairs, right? Right, we know we can't do SN2 reactions, right? Why can't we do an SN2 reaction? Tertiary. So you've seen leaving groups, right? All the leaving groups we've looked at have been chlorine, bromine, and iodine, right? Could this water be a good leaving group? Right, this is like water. Could that be a good leaving group, you think? Absolutely. Now it is, right? We've made it better, right? Alcohol turned into this OH, turning into a water, makes it a good leaving group. So now it can just leave. Yeah. So now we have a carbocation, and it's a tertiary one, so that's good. We have water. We have Cl minus. So was the first step the rate determining step here? The second step, right?
How do you know which one's the rate determining step?
So I look at right here. So making this isn't that unstable. But forming a carbocation, we know this is going to take a lot of energy to form a carbocation. Because carbocations, right, don't have full octets by their very nature, are very unstable. Right? So that's why I wanted to caution you guys about SN1 being one, or SN2 being one step, SN2 being, or two step, all those things, right? Just stop and think about what's going on, right? Don't try to memorize how many steps they are. Think about what the rate determining steps are always going to be. Right? So then the final step here is this chlorine just attacks that carbocation. And we end up with T-butyl chloride and water. Did we balance our charge? Hope so. It's all neutral again. That's our final product. So the different thing here is we learned about a new leaving group, essentially. Right? Water could be a leaving group. But we've done it this way before, plenty of times. So now it's just going back this way. So water can be a leaving group, and that's actually chapter 11 stuff. Start doing that stuff too. All right, let's look at 20 and 21. I think they have the same. They're kind of getting at the heart of what is part of the rate for SN1 and SN2. So 20 has T-butyl chloride in two cases. And methanol, same temperature, all that stuff. What they change though is they say this is 1.5 molar, this is 1.5 molar, and they say there's 30 mils of this, and there's 60 mils of this. And then they ask you what the products are, and then they also ask you predict which reaction the repair will occur at the faster rate, or faster rate, slower rate, same rate. So what kind of reaction are we dealing with here? What kind of alkyl halide do we have? Has to be SN1, right? So we already know for 20 at least, in this case, we know this is an SN1. So the products you should be able to look at and draw pretty fast now. Just the organic product, so I'm not, there is obviously a chlorine somewhere, right? Cl minus and a H plus. Yep. So that's good. We have the product, same product. Is the rate going to be any different for either of these? So what's different about, is the rate going to be any different for either of these? No. Right? Because what's the rate for an SN1 reaction? What's the rate for an SN1 reaction? Rate is equal to K, or rate constant, times the concentration of the alkyl halide, and nothing else. The nucleophile doesn't matter. So adding more, changing, right, this is the same concentration, 1.5, 1.5, but adding more of the methanol in this case, does that change the rate at all? No, it's not going to affect the rate at all. Right? So they're both going to be SN1, same rate. Right? The rate doesn't change with having more nucleophile for SN1s.
More of the, like, if there is a difference between.
If there's more of this, if it was more concentrated, then there'd be possibly more of this happening.
It's just more barbarity with the...
Right. But I don't think it'll change. Yeah. So, well, this, right, essentially the nucleophile doesn't affect the rate for SN1. Now let's look at comparatively number 21. So if I move some of this stuff up. Now let's take a look at 21, which is a little different. So 21 now has propyl chloride, and it has methoxide, O minus, and DMA is a solvent. It should be in the bottom of the arrow. That's on the top of the arrow. That's okay. And it's saying 0.1 molar, and here it's saying 0.2 molar. So again, you have to ask yourself, what kind of alkyl halide do we have? Primary. So what kind of? Has to be SN2. So we know they're SN2s. Remember what the rate for an SN2 is? Rate equals K times the concentration of the alkyl X of the nuke. Good. The product of this reaction is going to be the same for both. Did I lose a carbon? Hope not. Same for both. The question is, which one's going to have a faster rate, same rate, slower rate? So what changed here? We have 0.1 molar, 0.2 molar. So this has more nucleophile, right? If you have more nucleophile, what's that going to do to the rate? It's going to make it, this one is going to go faster because there's more of this around, and that you add that right into the rate equation. Boom. All right, number 32. This one's kind of set up nice for us, but it has a piece that maybe we forgot about. H, and then this D going away from us. Remember what D is? D was deuterium, right? So it's a hydrogen with an extra neutron. But that is a different thing, right? So when we're trying to figure out stereochemistry, right? Remember we needed sp3 hybridized with 4 different things. So D and H are different things. So now this is, right, a stereo center. And so what they're going to do, they're saying we have NaOCH3, and we're doing this in methanol. So this is kind of a classic condition sometimes. You'll see this. Remember Na plus, right? They won't say it, but it's Na plus O minus, right? So is this a good nucleophile? Is this a reactive nucleophile? Yep, O minus, right, negative charge. We're still in a polar protic solvent, but if the we're in a polar protic solvent, right? Methanol, there's a hydrogen bonded to this oxygen. That's a polar protic solvent. But let's think about this though. This is why solvent choice matters sometimes. If I have methoxide, if this reacts with the solvent, what does it make? The same thing back, right? So if I did this reaction in ethanol, I could be in trouble though, right? Because then I would make ethoxide, right? So everybody see how solvent choice is really important here?
You want to say that slower?
So let's try. Okay. O minus CH3, methoxide. If this methoxide reacts with the solvent, what do you make?
Oh, yeah.
You make methoxide again. So it's not that big a deal. Now, but think about this though. Is it important that you chose methanol as a solvent? Because if you chose ethanol, what would you have made? You'd have made ethoxide. But you want this to be your nucleophile. So you gotta be careful about solvent choices. That's all I'm trying to point out. Right? So even though it's a polar protic solvent, it still works just fine. Right? Even though, remember what I've been telling you, SN2 doesn't want polar protic solvents. Right? Because your nucleophile will react with the solvent. But here's a special kind of cool case where, so what? If it does, I'm just making back what I started with. So it's okay. You see that? So, what's going to happen now, it's an SN2 reaction. Our leaving group is in the plane, so it's already there. So we can draw the mechanism arrows. It attacks. Kicks up. Now, do we need to change the wedges and the hatches here? I don't think you do. You can just draw the OCH3 here and the methyl group there now. And you can just leave the H's and the D in the same spot. But you see how I switched it around when it came through here? This methyl group had to come up. And now the OCH3 is here. Because remember, SN2 is a backside attack, right? And now to double check ourselves, if we did this correctly, we should switch stereochemistry. Let's do R and S for the starting material. So we got to rank our people. So what's the lowest ranked? 4. What's the highest ranked? Bromine. And then deuterium's 3. This is 2. So 1, 2, 3. That is
1, 2, 3, 4, 6, 7, 8, 9, 10.
R. That means this better be S. So let's check. Let's do our numbering again. So this is 4. This is 3. This would be 1. This would be 2. So now it's 1, 2, 3. Now it is S. Right? Always double check. Right? But this is a nice way to double check ourselves. Right? So some people will be worried about drawing it incorrectly. Rightfully so. But you can always go back and check your model and say, wait, I drew it right. As long as I made it S, I drew it correctly. Right? Because there's lots of ways you could draw this. So it's a good way to check.
When you don't show the stereochemistry, I noticed we don't, it doesn't matter as much how we.
So yeah, if it's not a stereo center, then it doesn't matter. Right? If there's not 4 different things, then it doesn't matter at all. Right? Be careful with rings though sometimes. It may be important. Number 33. This is a good one. So this one says ethyl acetate can be prepared by an SN2 reaction. Draw the alkyl bromide and nucleophile used in the reaction. Remember to include formal charges. Do not include counterions. So this is your classic retrosynthetic problem. So we have ester. So the thing you need to think about, they're calling it an alkyl bromide and a nucleophile. So every reaction, everywhere, ever since forever, have always involved 2 things. What 2 things? Nucleophile and electrophile. So we have a product here. This product had to come from a nucleophile and electrophile, and that's what they're asking us to figure out. So when we try to figure out those pieces, what we need to usually look at, though, is in this molecule, which bonds are the most polar? Which bonds look like where reactions will take place? So I'm going to number the carbons. 1, 2. I'll number the oxygen. 3, 4, 5, and I'll make this 6 up there. Which bond do you think is the most polar, most likely for the reaction to take place at?
I think two.
Oxygen, that makes sense. Oxygen where? Which oxygen and which bond and which one?
2, 3.
Oxygen 2 to 3. Okay, let's look at oxygen 2 to 3, that bond right there. So what do you guys know about esters? What else can they do? In an IR spectrum, which you learned about,
Yeah.
the C double bond O in esters is actually not always doesn't have that much alkene character. It actually has the frequency is actually
Single bond.
longer than you think it'd be. It's like 1740, right? Now why is that? Because there's some resonance. Let's draw those resonance structures out to see how strong that bond between 2 and 3. Because you guys are saying the bond between 2 and 3 should be weak, right? Because that's the most polar bond. Well, let's see what resonance has to say about that. I can push electrons this way, right? So that bond between 2 and 3, is that a strong bond or a weak bond, do you think? Stronger than you thought. And maybe if you look at this resonance form of this ethyl acetate, is there a bond here now that you'd feel like is maybe weaker? 3 and 4. Absolutely. So 3 and 4 is where we actually want to break it.
And why would 3, 4 be weaker?
Because now if you look at this resonance form, there's a plus charge in this oxygen. And does oxygen like to have a plus charge? No, in reality, right, this oxygen is more electron rich. That makes this carbon more delta plus.
And that it wouldn't make the carbon 2 delta plus because.
Nope, because now you're right. If you're talking about the bond between 2 and 3, carbon 2 is delta plus. Don't get me wrong, but the bond between 2 and 3 is not the weakest, most polar bond, right? Because of this resonance form, there's actually double bond character there.
Okay.
So if we say the bond between oxygen 3 and carbon 4 is the most polar bond, we're going to separate those two things out into an electrophile and a nucleophile. Which part of that bond that we formed, which part do you think was delta minus originally? The oxygen, right? Make that delta minus. That means carbon 4 needs to be what? Okay. So the carbon 4 and 5 will be part of what? The electrophile or the nucleophile? The electrophile. How do I make carbon 4 delta plus? What do I need to put on carbon 4? They tell us they want an alkyl bromide. So I'm going to make carbon 4 have a bromine. Right? 4 and 5. And now for the other piece, what should I do with the oxygen? Should I put the oxygen having to make it a good nucleophile, might as well have a minus charge, right? And when you bring these two things together, you can do an SN2 reaction, right?
Oh, that's right. Yeah.
It's a little tricky, right? But it's a good retrosynthetic way to start thinking about working backwards, right? Where do these bonds come from, right?